Good afternoon. It's now 4:30, and let's start. I'm expecting some more students, but Mr. Vailin tells me that he has a lot of, slides to go through, and we should start as quickly as possible. Anyhow, for those of you who do not know me, my name is Ali Kujuri. I'm an adjunct professor at the Engineering Science Department and one of the organizers of this lecture series. I'm thankful to Mr. Sharon Mariwani and also Chait Lab, who are helping me in the organizing of this lecture series. On behalf of the department and the School of Science and Technology, let me welcome you all and also our speaker to this third lecture this academic year, and believe it or not, 138th lecture since we started this lecture series in 2006. Look now, it's good now. We are now 12 years now doing this, right? How about that? That's good. So before I introduce our guest speaker for today, let me mention that there'll be, Kate has ordered delicious pizza that's going to arrive at 5:30, and our guest speaker for 2 weeks from now is Mr. Benny Smith. He's a consultant as Vision Smith, and the title of his talk is LED Lighting, Cool and Bright. Okay. Mr. Whalen graduated from University of California, Davis in 2012 with a master's degree in electrical engineering. After graduation, he joined National Instrument as a radio frequency hardware design engineer. He has been working as a designer and has had roles in characterization of and verification of the high performance vector signal transceiver products at National Instrument. So here is Whalen.
Hi, everyone. Thank you so much for joining the presentation today. And today we are going to go over some of the basic RF fundamental and terminology. So when you really feel interested in RF, you have to learn a lot of different terminology than general electrical engineer subject. And the RF world is totally different than analog and digital. It's more like a cell technology based world. So there's a lot of terminology and RF measurement you have to learn and get and know a little bit before you join this industry. So today, let's go over the agenda. I will go over some of the RF basic terminology, and then I'll talk about some of the modulation in analog and digital, and then go through some of the basic RF measurements, and at the end I'll go over some of the traditional and general RF measurement instruments like a vector signal analyzer, generator, and network analyzer, VNA. So what and why? So what RF mean? So RF is mean radio frequency, and generally it's a high frequency signal. So typically associated with wireless and modulation, but usually you heard the most RF and microwave. They are particular cover a different frequency range, but there's no strict definition. So you see the RF is cut down to a few kilohertz up to 26 gigahertz, and microwave can start from 10 gigahertz up to 100 gigahertz. So people will always say, I am an RF and microwave engineer. So that means they are design products cover frequency from kilohertz up to 100 kilohertz. It's a really broad range. But you can say RF is more like a little bit lower frequency than the microwave. And so when we talk about RF and microwave signal, right, there's some of the rules we have to follow. Like C equal F times wavelength. The speed is constant value. So that means you're going higher frequency, your wavelength is smaller. So this is the rule you have to follow. So that means you go on higher frequency, you require lower wavelength, you have a smaller antenna. So So what is RF system means? So in RF system, they can be used in a lot of different areas. Let's talk about the wireless. So in the wireless, there's an industrial communication, like the cell phone, and all like the RFID circuit design in communication like cell phone, like point-to-point link, like different satellite station to different satellite station, and broadband like FM, AM, and TV, different radio frequency, and in WLAN it's like 802.11 stuff like what the Wi-Fi we have been using all the time, and like the telemetry, and in cable we have cable TV, modem, and DSL, and beside those two areas also have radar, like signal spectrum monitoring, and instrumentation and microwave often. They're all related to RF system. So how the simple full RF communication system works? So we always start with the baseband, right? Baseband means the low frequency signal like analog signal, and we digitizing and sourcing and doing the channel coding. And after we doing the modulation. Modulation can be I and Q signal, and we doing up converter through the antenna. And we in the receiver side, we using the antenna to receive the signal and doing down conversion, and doing the demodulation, and get back to the digital signal and get back to analog. So it's the whole system from baseband to high frequency, and receive from the high frequency back to low frequency. So let's take a sample at the cell phone in the wireless transceiver. So in the cell phone, inside they have a baseband processing, digital signal processing IC, and it's using all the signal in digitalizing and doing the transmit change to the up conversion, to send out to the signal tower, and then the signal tower sends signal to the receiver chain on the cell phone and doing demodulation and down conversion and back to the baseband processor. It's the same idea as the previous slide. So why we using RF for communication? People will ask this question a lot of time because remember C equal frequency times the wavelength. So you have higher frequency, you only need smaller antenna. And when in recent industry, most of the electronics product, we try to make smaller and smaller, right? You're not going to bring a really big old school cell phone to every day. So in order to fit in a small antenna, you have to use some of the very high frequency signal. And more high frequency can support many communication link because higher frequency can support higher bandwidth, and higher bandwidth you can have more processing of data acquisition. So for example, you have a signal tower, you send an RF signal to your receiver, like a cell phone, and cell phone using the antenna to receive the signal, and all the RF signal, they can using a general sinusoid signal to represent it. And in RF frequency, there's a multiple band. And the RF frequency band was controlled by country, so different country have different band. And here's some of the general frequency band. It's not exactly the same in different countries, but they are really close. So like the industrial, scientific, and medical, they are license free. So those frequency range you can use for free. It has been used in education as well, most of the time. So students can use those frequency range to do their lab work in school for free. And cell phone usually using 800 MHz or 1.8 to 1.9 GHz. And GPS is about 1.6 GHz. And cable TV is about 50 MHz to 850 MHz. Again, those frequency range is slightly different from country to country. Okay, so as mentioned, the frequency band was controlled by government, and this is the current US frequency allocations. And you can see this color chart have been really, really packed. This frequency band have been used for many, many years, and like this AM radio, TV, broadband, FM radio, those have been used for many years ago already, right? And Wi-Fi have particular frequency range. And since more and more technology development, we need to find some of the frequency range we can use. and still has some unlicensed frequency band. And if you zoom in, it's here. There's some area over here with a 60 GHz unlicensed. It has been used for WiGig, like the AO211 family signal. It has been what the WiGig means is I will go through later on. It basically just have a really wide instantly bandwidth for data acquisitions, for video streaming. It will make way faster. So you zooming in, the 60 gig unlicensed band is around here. So this is what the current industry have been using it. And different countries have different location, right? I mentioned. So in China, for this unlicensed spectrum, it's allowed from 59 to 64. And Japan is a 59 to 66. And USA is a little bit wider, allowed from 57 to 68 gigahertz bandwidth. I mean, 57 to 68 carrier frequency, up to more than about 11 gigahertz range. Okay, so let's go back to the AO211. This is the IEEE's wireless standard evolution. So all the AO211 standard is defined by IEEE. And from back to 1997, the first AO211 is only 2 megabytes per second. It has been used for internet. And another year is AO211B, 11 megabytes. It's used for email with 2.4 gigahertz. And if you go up to the latest one, it's AO211I. It's a 27 megabyte with 10 megahertz bandwidth with 5.8 gigahertz carrier frequency. And also in the middle of the evolution, we have the latest AO211AD. It's called WiGig. You can see the data streaming can go up to 6.76 gigabytes per second. So they can do a beamforming and with 2.16 gigahertz bandwidth. And the carrier frequency is around 60 gigahertz, the unlicensed band. So with this wide gigahertz, have a really high rate throughput. So a lot like a homing, in-home studio and data streaming can really fast with this 2.1 gigahertz bandwidth. In a simple word, you say the bandwidth. What the bandwidth means, just like you have a highway. It depends how many lanes you have to go through the vehicle. So it used to be maybe a single lane, right? But now in WiGig, you can say we have 100 lanes in parallel. So you can go way more vehicle than used to be. So this is what they call the high rate throughput. But since WiGig is a really good subject and people, industry always like to use it as much as possible, but they have some of the facts we had to deal with. So some is the cell phone, the cellular intercept system. So in suburban, most of the cellular intercept system is about 1 to 2 miles. And in urban, it's about quarter to half mile. And what's the 5G cellular intercept system? 200 meters. Really, really short. Why? Because I go over later. So what the AO211AD, the 60 gigahertz Wi-Fi cover area? 10 meters. So you have higher and higher frequency, your transmitter distance is smaller and smaller. So you have limitation. So there's also have a calculation, a statistic about what percentage of the cell phone use most of the time. 75% of the people using the cell phone indoor. When I say indoor, it means you're probably inside the train, inside a bus, and inside, it's not outdoor. Outdoors means you're outside the building, right? So 75% of the people using cell phone indoor. So we probably 10 meters should be good enough. And so based on the statistical analysis by 2017, how many number of AO211AD device used will be 1.7 billion. So the WiGig is a really good area. People try to put a lot of money to investigate. And back to this slide, why is only 10 meters? Remember, for this Y gig, it's a 60 to 75 gigahertz carrier frequency. And in higher frequency, your signal will be absorbed and degraded a lot by the air. So you need to allow a huge amplifier to amplify the signal in order to send the signal to the destination. And 10 meter is about 33 feet is the limit. If you send a Y gig signal more than 10 meters, your signal will be not efficiency to receive. So let's talk about what the electromagnetic waveform propagation look like. So in RF signal, right, there's a two field. One is the electromagnetic wave. So the vertical is called magnetic field, and the horizontal is called electrical field. And the electrical field is, you can calculate the wavelength. Again, the wavelength is determined what the RF frequency you're going to use. So higher RF frequency, your wavelength is shorter. And then you can use a smaller antenna to receive this signal. So let's talk about the wavelength. So in low frequency, let's say 1 megahertz, your wavelength is about 300 meters. And because it's a very low frequency, your voltage is almost same along the short transmission line. Because you consider this is a sinusoid curve signal. If you have a really low frequency, that means your wavelength is really big, right? So per voltage change in distance is really minimum. So you can consider it's like a constant voltage in very small transmission line. But when you go to high frequency, it's a different case. Let's say 1 gigahertz, your wavelength is only 30 centimeters. So that means your voltage is a function of distance, or your cable, or your transmission line. So in dealing with different frequency, you have to consider a different power definition. And this is one of the key in RF. So what's the RF versus not RF measurement? So traditionally, in not RF measurement, we usually just talk about voltage and current. Again, in low frequency, the voltages are really same in different distance of the transmission line. But when you talk about RF, the voltage and current are not consistent with distance, right? Because it's a sinusoid signal, and also it depends on your frequency. But the power is constant. So this is why when we talk about RF measurement, we always deal with power. We don't talk about voltage and current. So if you're working in RF, you heard about the more we talk about power, and you heard someone talk about voltage and current, that means they are not working in RF. Okay, so here is an example to show how the power flow requirement, because all the power transmit and receive, they have a impedance media, right? So let's say this is your impedance plane. You transmit a power to this interface, and not all the power can go through the receiver because you have impedance mismatch in real work. So some of the signal will reflect back. So we only can get certain of the transmit power going through, and some of the power will reflect back to the generator side. So this is what the concept called impedance. And the perfect matching impedance means 50 ohm. So you heard about mismatch impedance. This is the lead to the power level fluctuation, which causing the reflex power. So here is an example to show how the RF signal look like. When we talk about RF signal, we also talk about in time domain and frequency domain. And you can consider this like a free axis charge. Let's say the vertical is an amplitude in power with RF. And this direction is considered is a frequency, and this direction you consider in time. So if you look through from the time side, if you look through the plot with amplitude versus time, we will look like this, right? But you're looking from the frequency versus amplitude side, it looks like a single pole. So this come up to be different displacement when you talk about in frequency domain and frequency domain. So consider a single sinusoid signal. In time domain it look like this, but in frequency domain it look like a single pole frequency. And the x-axis will be in frequency, and this side will be in time. So why we talk about frequency domain? Why we create a new definition, right? In RF, just because in time domain, because it's a sinusoid signal, you not really see a lot of information. All you see is just the amplitude and the absolute amplitude in different time. However, when you go to frequency domain, remember in the perfect sinusoid signal, in frequency domain will be a single tone with a particular frequency. However, most of the frequency they have harmonic products. So let's say you have a CW signal, have a lot of harmonic distortion issue, you won't be able to see it in time domain. But when you're using frequency domain, except the main tone, you will see different harmonic signal. They can tell you how bad the harmonic distortion and give you more insights. So in communication measurement, how are we going to characterize it? So let's say you have a signal with frequency domain, right? And this is the frequency range, and the channel is mean the middle of the center frequency with a certain amount of bandwidth. And outside of this certain bandwidth, you can also measure the adjacent channel. So consider the signal transmit in air. You're never able to filter out all the signal interference to you, right? So you have to deal with some of the adjacent channel signal with your majority base channels. This come up to some of the communication measurement requirement. So in the industry, we talk about modulation. So the adjacent channel, how much interference to the main channel, we call them the modulation quality. And to determine how good the signal in digital modulation, we usually using two main definitions. One is called EVM, error vector magnitude, and one is called modulation error ratio, MER. These two are the standard to tell you how good the modulation signal when you're doing communication measurement. So let's talk about the modulation. So modulation can be analog modulation and can be digital modulation. So this is the general formula for RF signal. So the A is mean the amplitude, and the frequency is inside the cosine FC, and you have phase. So all the modulation scheme will change one of both amplitude or frequency. Frequency plus the phase called angle. So all the modulation is trying to change these three elements. And they have different definition and they have different benefit. So let's talk about in signal level. So you see this is in time domain, right? It's a sinusoid signal. And if the starting point is not start from 0, that means your phase is not 0. And your horizontal amplitude value is go through on a 0 is mean the amplitude. So we remember when we talk about RF signal in amplitude, we talk about power. So the unit is a watts or dBm. It's not voltage or current. And the period is going to calculate the wavelength of the signal. And the frequency, f is equal 1 over time period, right? And the omega is equal to pi f. So before I talk about the modulation, so the first modulation I want to talk about is the amplitude modulation. So when you say amplitude modulation, that means the signal is changing by changing the amplitude of the signal. So you see the message is the red line, and the carrier is the inside high frequency signal. This is what the AM modulation signal look like. Beside the amplitude modulation, amplitude modulation is mean AM. So this is what the AM radio using signal transmission. and changing the amplitude. And also another frequency modulation called FM, so it's frequency modulation, changing the frequency. And another one's changing the phase. So those three are the majority analog modulation method. And now we are using digital in the industry the most because the digital modulation is more robust and easy to transmit and easy to process in the computer. And the difference is instead of changing the amplitude and frequency and phase, we are using 0 and 1 to represent amplitude, frequency, and phase. So we just try to digitize all the analog information. And the first one is called ASK, amplitude shipping keying. So we are trying to using 0 and 1 to represent a different amplitude. And we see here this amplitude represent 1, 0, 0, 1, 0, 1. And same idea, we're using the phase shift keying, it's called PSK. We're using 0 and 1 to represent a different phase value. And the last one is a FSK, called frequency shift keying, using 0 and 1 to represent different frequency area. So in digital modulation, there's many different times, but they have a particular naming decoding ring. So Q is mean quaterary, is mean M equal 4, and binary is mean M equal 2, A is mean amplitude, shift is mean S, and keying is K. So let's say ASK is mean amplitude shift keying. So when you know the decoder naming style, you can easily to define what the ASK mean. Same thing for QAM, quadratic amplitude modulation, and the quadratic M can be a different binary, like 4-bit, 8-bit, up to 256 bits. It depends how much the bandwidth and how you want to do the signal modulation. So why so many modulation schemes? ASK, QSK, QAK, a lot of different names, right? So different one have different efficiency trade-offs. When we talk about the modulation, we talk about their spectrum, their power, cost, size, and reliability. And each one have a different constraint. So some signal can easier to use in mobile terminal, and some signal can be easier to use in base station. So different station or different requirement prefer using different modulation methods. But they all build from the same building block. Remember, all the modulation signal try to change the amplitude, frequency, and phase. So let's talk about the I and Q. Remember, most of the analog signal we try to digitalizing and doing modulation and demodulation, and then doing up conversion and down conversion. And in the middle of doing all the signal transferring, we have a concept with I and Q. What the I and Q mean is, assuming you have a signal, you try to separate the signal with I element and Q element. So this is how it changes. You see, remember this is a general RF signal formula in sinusoid format, and you can do the math to separate two sections, right? And then you can use an I to represent the cosine and using a Q to represent sine. And by doing this definition, you can generate a new signal format using I and Q. And there's a reason why you want to do that. So going back to here, when you're doing the transferring from single cosine formula to I and Q plus cosine and sine formula, it captures all the information we want. You have including the amplitude and phase information. So by changing the formula, won't hurt anything. We still keep original information, and it gives us some of the benefit. Is most of the time you measure the amplitude is very easy. Amplitude is just power, right? But measure phase is really difficult because you have to get a really phase coherent system to capture what the original signal phase value, and by the time you measure, the phase probably shift. So using I and Q definition can tell you what the phase change during the transmission. So this is one of the main benefits of using I and Q signal to represent. So let's go back to discharge. So assuming we already know we can separate the signal to I and Q value, and I is mean in phase, right? Q is quadratic, and doing modulation, you heard the mode is called constellation diagram. What the constellation diagrams means when you have an I and Q signal represent this dot, and you do a multiple I and Q signal transferring, you have multiple dots in your constellation diagram, and each dot will communicate each other, and the more dot the signal transferring requirement will higher and higher, and the bandwidth will be higher and higher. So going further, it's called ASK. Remember the amplitude shift keying? So for this example, we only say, let's say 1 bit per simple. So only 1 bit changing, 0 and 1. And you will only see in 2 dots. One is out, one is 0, 0, 1 is 0, 1. And going to here, the conjunctive modulation. So the conjunctive modulation can be multiple simple, right? So what the simple mean? So you have 4 simple, that means you have 4 dots. And each dot is represented by 2 bits. So 2 to the power of 2 is 4. So let's say you have per simple you have 2 bits, you can create 4 simples. So in the chart you can see 4 dots, and all 4 dots will be communicating each other to represent a different scheme in time domain. Let's say you have 2 bits, so you're using 1 CLO for a particular area in frequency, and using 1 1 or 1 CLO or 0 1 or 0 0. Using these 4 to represent a whole signal you try to transmit. Remember, you have higher simple, you can use more bit to represent particular frequency to give you more robust to send the signal. So you can send more data. You have 4 simple, you only can represent four area, right? So you only can send particular amount of data. But you have 100 simple or 256 simple. That means you can use all these simple to send more data. So this is the example how the constellation diagram look like. So this constellation is only 4 simple, right? So each simple represented by 2 bits. So 0, 0, 0, 1, 1, 0, and 1, 1. So they all talk to each other. More look like a I diagram in analog world. But in RF modulation world, we using this diagram to talk about the IQ and the modulation signal quality. And this is called constellation diagram. So here's an example of the constellation plot. So have 4 simple. So each simple has 2 bits. So you can say it's a 2 bits per second. So it's a 2 hertz. So you have more simple, you can have higher frequency, you can transmit the signal. So this is why more simple can give you more bandwidth and can do signal acquisition and transmission much faster. So this is why you have a concept called QAM4, QAM16, up to QAM256. So the number of 4, 16, and 256 is dependent how many simple you try to do in the modulation. Why is it getting challenging when you have more simple? Let's say you try to transmit signal and you have so many simple, right? Each symbol, they can be talk to each other in the way you want to control or in the way you don't want them to do it. So sometimes some concept called crosstalk. So let's say you don't want to these 2 signals talk to each other, but in real world they do talk to each other. So this is why the concept is crosstalk. So when you see in this constellation diagram, you can determine how good the signal and how or even how bad they have crosstalk. And this is why people try to use this diagram to do a judgment about your digital modulation signal quality. Okay. Before I talk about why we're using I and Q to do the signal transmitter and receive, and here's an example how we going to generate I and Q signal. So you remember the I is mean in phase, the Q is a quadratic, so they have 90 degrees phase shift. And this and when we separate the signal to I and Q, they can do the analog or digitized conversion myself, and eventually we can add them together because we know exactly they are 90 degree phase shift. So here's the example. So we have original I and Q digital signal. We try to do the D to A conversion, so change the digital to analog. And with analog signal, we go through the mixing. We can up converter to some of the modulator I frequency. So this is the first step. We start from I and Q and going to do the IF conversion. And further, we can either break the step. We can consider the modulation conversion just like an intermediate frequency step. We can add another mixer to up converter the frequency to even higher. The reason to doing it because if you're using a single step conversion, you don't have a lot of capability to do filtering. Because all the signal, remember, we try to generate a really clean signal, but signal can be interrupt to other signal, right? Like adjacent channel. So you kind of up convert the frequency to a particular frequency and using a filter to filter out other signal you don't want, and generate the final modulation signal you want to transmit. And here's another example to talk about the constellation diagram. So this is a 16 quam. 16 is 16 bits, right? So it's a 16 simple. So it's 16 simple. So and you only need 4 bits to represent 16 simple because 2 to the power of 4 is 16. And same idea, 64 quam is mean you have 64 simples, and you only need 6 bits per simple to generate 64 simples. And you have more simple, and your simple rate is lower. I mean, when I say simple rate, it means the bit rate is only 1/6 because each simple requires 6 bits, and each bit rate can be 1 divided by 6. Okay, so in modulation, using in the industry, you might heard some of the name called FDMA, TDMA, CDMA. This is the current modulation scheme used in cell phone. We probably heard about the CDMA the most. So they have different names. So the FDMA is mean frequency division multiple access, and CDMA is mean code division multiple access, and TDMA is mean time division multiple access. They're using a different modulation scheme. You will see the spectrum, right? Remember, RF signal can be represented in time domain and frequency domain. So for FDMA, the main easy to recognize the F is mean frequency. So that means all the signal you try to modulate is based on frequency. So this is why you see this side, you see different color code represent different frequencies. And when you talk about the TDMA, it means time division. So all the color code represent different signals in time domain. And in the frequency domain, they look the same. And in CDMA, it's a code division. That means they actually using a different signal with different power to represent. They look the same in frequency and time, but they look differently in power. Because you can use a 0 and 1 to represent different power. So the other term is called OFDM. Remember going back, FDA? So FDMA is a frequency division multiple access, right? OFDM is called orthogonal frequency division multiple. It's also used in the cell phone the most. And they have benefits. Remember, different scheme modulation have different benefit. The way to do using the OFDM because you can send multiple carrier signal, and you can put each signal in particular frequency, and let their start at the particular frequency next to next carrier. By that time, the interference to each carrier will be minimum. So they force the signal in particular F1 to F6 frequency, like for sub-carrier modulation. So this is why they call OFDM. The benefit of doing this way, you can minimum the interference with multiple carrier signal transmission. Okay, now I talk about some of the basis of measurement. So remember, in digital modulation, the most important name to define the modulation quality is called EVM, error vector magnitude. And it will tell you how the individual I and Q data quality, like their amplitude, their alignment. So this is the number you're going to expect, like how good your signal using in modulation. And other terms called MER, modulation error ratio. This one is a more like a signal to noise ratio. This most likely telling you how strong the signal you're going to measure. And it's not as good as the EVM to determine how good your signal. The EVM is like a main quality control parameter you're going to spec to determine your signal, because if your device have a really big distortion and have a lot of noise or amplitude accuracy, your EVM number will degrade a lot. So people try to use the EVM to diagnostic your system. So back to the EVM. So how the EVM calculation, right? Remember in the constellation diagram, each dot is represent each symbol, and in idea, you know your simple second location, right? Because you know your magnitude, you know your phase. But however, when you transmit the signal or when you receive the signal, the actually dot is not located to here. When you measure it, the dot probably located to here. So there's some of the error in between your real IQ signal or your major IQ signal. So that's come up with a definition called error vector magnitude, because we talk about the I and Q, all the signal is a vector based. So it can be a magnitude error, it can be the phase error. So this come up with the concept called EVM. And in IEEE and 3GG, they have a particular definition. They have a requirement for different modulation scheme. So you see here, there's many modulation scheme from BSK down to 256 QAM. And each one have a requirement about the EVM number. So like say, oh, for BPSK signal, you only need the EVM number better than 5 dB. But if you have a 64 QAM signal, your EVM number need to be better than 25 dB. So the industry try to follow this minimum requirement to design their device. And this one just the general requirement doesn't mean you only need to hit this requirement, right? In rule of the thumb, you only need to be 10 dB better than this number. So let's say you are a vendor, you try to build an IC to generate a 64 QAM signal. You'll need to hit the number at 35 dB, not 25. You have to be 10 dB better than the 3GPP requirement. And even more challenging when you try to develop your tech equipment, because the IC design need to be 10 dB better, but in order they measure 10 dB better, they need a tech equipment to measure their IC, right? So the tech equipment need to be 20 dB better. So let's say Apple have a cell phone, try to send a signal with 64 QAM. They want to measure their cell phone can have a 25 dB better. They have to use an IC with 35 dB in spec. And the IC need to be using a tech equipment to measure 45 dB. Okay, so let's talk about some of the modulation issue. When we talk about the modulation, one of the term you heard the most is called IQ impairment. Remember, all the modulation is based on I and Q format. And when you have an I and Q analog to digital generation or digital to analog conversion, you using a phase shift, right, with a local oscillator, and then mix them together to generate a modulator, IF or IF signal. Each parts of the hardware can contribute some of the issue. Like say the I and Q on the analog and digital side can cause a DC offset error. And your local oscillator always have phase noise. And you're using a local oscillator to do a 90-degree phase shift, have a quadratic skew, and your output have gain imbalance between I and Q. So when all four combined together is a generator called IQ impairment. So technically the I and Q should be perfect, but nothing is perfect in design. So this is why come out a term called IQ impairment, and they all come from these four particular area when we design the hardware. So back to the constellation diagram. Remember, the constellation diagram is the one of the most direct interface to telling you how good the quality of the signal. So this one you have a 16 QAM signal, right? If you have a gain imbalance, that means your I and Q amplitude is not identical, and you kind of seeing they are trying to stress. They are not like a rectangular. You see the vertical is longer than horizontal. That means your I amplitude and Q amplitude, they are not very close to each other. They are different value. So this is why called gain imbalance. Right? And when you talk about DC offset is mean they don't have a you see here the I and Q term, the I maximum and the minimum, their variance is not the same. They don't have a consistency peak value and the minimum value. So you kind of see in the constellation kind of rotate. It's not a perfect rectangular box, right? They kind of rotate on this side. And another issue, quadratic skew, they kind of rotate other side. So these two are really easy to mess up. You probably say, oh, this one maybe come from the DC offset, and this one come from the quadratic skew. But they both symptoms is so in the constellation diagram is they are not perfect aligned in the center. They try to be towards to one side or the other side. So when people debug, they usually just see the constellation diagram first and telling you the UAM signal is good enough or not, and then they can go further in diagnostic in particular area. Go back to here, particular area can contribute a different issue, right? Like gain imbalance is mainly the amplitude. So you can make sure the I and Q signal they're the same. So this is the first step, you try to debug and diagnostic. Okay, so there's another term called Chris factors in IF, especially for modulation signals. Remember, in modulation signal, the power mean the amplitude is always changing. So when the power is changing, there's a concept called peak power and average power. They are not the same. So the difference between peak power and average power is called Chris factors. And some people will call PAR, PAR, and P is mean power, peak power to average power ratio. So this is why called PAR. The same kind of concept with Chris factor. So you see a signal, right? When in time domain, you see some area is low power, some section is high power, and when in the frequency domain, your CN is you can show in the averaging power, but sometimes you probably have a spike going up by a peak power. So between peak power and averaging power is a difference called the Chris factors. So another thing is adjacent channel leakage ratio. Remember, we have let's say we have a CW a modulation signal. The main channel is the bandwidth we try to capitalize, right? but they also have an adjacent channel, like upper adjacent channel and the lower adjacent channel. So assuming you have a perfect signal going to the receiver, but when your receiver doing the signal analysis, it's not 100% to recover the original signal. It has it could be some of the harmonic or distortion. So the final result you measure in your display is probably like a blue trace. And those blue trace is causing like this really big silo is a 3-order distortion. And the noise floor could go up as well because any single receiver or instrument have noise by themselves. So it can be mess up your original signal. So this is why the noise floor is going up. So back to the RF power. Remember the power is mean voltage times current. And we also know in RF the voltage and the power is changing. So the power depending on the time you try to measure. You measure longer, you have more power, right? So the power is mean you take the number of all period and averaging out. And consider a sinusoid signal. You try to acquire one period of the signal and you calculate your power in this particular period. It's not a constant value. So in RF power, there's a different terms. Some people call watt, and some people call dBm, and some people call dBc. There's a multiple terminology, and some people call peak to peak. But they are represent the same thing, right? Let's say your watt is your real power definition, and in RF we prefer to change that to dBm, and in analog or digital world they prefer using peak to peak voltage. And how come we have so many different terminology for power? It just gives you the benefit to doing calculation. So let's say here, in linear mode is mean you talk about anything in real power unit, like watt, right? And remember the power was changing in time. So it's also, if you're doing watt, your calculation is way more complicated than using dBm. Because any time you divide the power by 2, you can just using 3 dB in dBm calculation instead of using a really complicated number like 3.122 watt divided by 2, how many watt you have, and you can always use a dB to represent it with power drop or power gain. And the difference is just a different mathematical. So you have 1 milliwatt. If you amplify with 8, your output is 8 milliwatt, right? And but what happens if your amplifier is not an integer, and your input power is not an integer either? It way more complicated. But if you talk about dBm, you just using addition or subtraction. So you know your amplifier have 9 dB gain, and you know your input is 0 dBm. So you just add 9 to 0 dBm to equal 9 dBm out of your output power. So you don't need to deal with the divider and multiply. You only need to use addition, add and subtraction. So make the calculation way more simple. And this other topic called harmonic distortion. Remember the signal is a cosine or sinusoid signal, right? And let's say your input signal is perfect, but any analog device, they are not linear. In real work, they have multiple terms. So when you have multiple terms to deal with your input signal, your output signal will be multiple terms also, eventually. So this kind of a concept to harmonic distortion. So in frequency domain, you see your base input signal amplitude is A, right? So A is amplitude. But when you have a not linear system, your output can be A and also A squared to A to the power of 3. So it's a multiple signal shown in the frequency domain. So this is why the concept of harmonic distortion. And you don't want to have so many harmonic distortion when you're doing the signal analysis or transmitter, because those are the signal you don't want to generate it. And most of the time, the people care about the intermodulation distortion. So remember, you have when your input signal is not a single cosine, when your input signal is way more complicated, your output will be even more complicated, right? And you have so many terms. So which term you care the most? Because apparently you cannot take care about any single term. You only care about the term affect your performance and quality the most. So this come up to the intermodulation distortion. And the one, this called a free order harmonic. So assuming you have a 2 input signal, you go through a system, you will create a free order harmonic signals. And by math, if you drop the input by 1 dB, your harmonic signal will drop by 3 dB. And you know exactly where the frequency location. So this is what people call TOI. We use this one to consider how good your system, how linear your system. Remember, if you have a perfect input signal, you have an input signal, you have a perfect linear system, your output signal will be linear, right? But because your real system is never linear, so it's always generate a harmonic signal. And this called third harmonic intermodulation distortion is the people try to calculate how linear your system can go. Except the free order harmonic, we also have second order intercept point, right? Second order is mean you have a midtone. Your second harmonic is you mean the double your original frequency, and there's a particular formula you define the second harmonic intercept. It's also used to determine how linear your system can go. You see this chart, when your input is going higher and higher, your system eventually will compress, and so your intercept point far away, that means your input power will start distortion in a very high input power level. So that means your system can be linear in a higher power level range. So it's a kind of a parameter to tell you how linear your system can go. And this is the third harmonic chart. Same idea, is just using before you talk about the second harmonic singleton. When we talk about the third order harmonic, you want to use two input signal to calculate their third harmonic products. And same idea, right? You calculate the TOI point versus different input power. Is this point higher and higher? That means your system linear range is bigger and bigger. So let's talk about the phase noise. Remember, most of the local oscillators have phase noise issue. But what is phase noise? If you talk about the time domain, phase noise means their phase keep changing. So you have a sinusoid signal. Remember, the sinusoid signal have a phase element. When the phase keep changing, you will see the signal is not stable in scope. Like here, you see the signal is keep vibrating, like a fluctuation in phase. And some people call it jitter. But when you go to the frequency domain, you remember the single CW signal should be like a single pole, right? But in real world, they are not like a single light. They are look more like this, like a Christmas tree. So it depends how big your Christmas tree is, determine how bad your phase noise. So you have a really big Christmas tree, that means your phase noise is really bad. Okay, so why I talk about phase noise? Remember, we are relying on using the EVM to tell how good your system, how good your signal transmitter or receiver, and the phase noise can mess up your EVM performance. So remember, this is a constellation diagram, right? And each dot is a simple. When you have phase noise, and your actual amplitude is keep changing it. You're not like a solid dot in the middle. You're more like a cloud. So that means your signal have more error. Your signal amplitude or phase keep changing. And not like a single dot anymore, it's more like a cloud, so your EVM degrading. And this just like talk about why the phase noise matter in spectrum measurement, because remember you have a big Christmas tree, you try to measure the signal just next to the main signal, because your phase noise is too high, it will cover your low power signal you try to measure next to your CW, right? So if your signal is under the phase noise, that means you're not able to measure any signal next to the CW signal. So I talk about some of the basic RF measurement, like TOI, SHI, they all matter about how linear your system, and talk about the EVM, they talk about how good your modulation signal. Those are the terminology you heard the most, and you're working in RF. And also I talk about the power in RF is not in voltage, so nobody will say no voltage in RF. So now I want to talk about some of the RF measurement instruments. So different RF signal have a different instrument to measure or characterize. So there's a multiple instrument types. So one is the frequency counter, power meter, spectrum analyzer, vector signal analyzer, and high-speed oscilloscope. They are receive signal, so they are doing signal analysis. Why there are so many? Because just for example, for spectrum analyzer, you only can measure a spectrum signal like CW mode. You're not able to do any modulation analysis. So when you do modulation analysis, you have to use a vector signal analyzer. And like using a high-speed scope, you probably measure in time domain the most. But you want to do a frequency domain, you probably want to use a spectrum analyzer or vector signal analyzer. And same idea for generating signal. You can generate a CW signal, like a single sinusoid signal, right? And you can also generate an I and Q modulation signal. So this come up to be a frequency synthesizer, a vector signal generator. And frequency synthesizer more like LO, local oscillator, to use in mixing product, in up converter and down converter. And the last one is the network analyzer, VNA. They can be used for both. They can be used for generating signal or receiving signal. So there's another term called vector signal transceiver. Transceiver is mean transmitter plus receiver. It's just using two terms add together. Okay, so just using the spectrum, using the receiver to doing a comparison. Each one has their different benefit, and like I say, using a power meter, the accuracy is really good, but they cannot do a lot of modulate. They cannot do modulation measurement, and their measurement is only good for power. It's very limited, but they are perfect for power accuracy measurement. And same idea for the frequency counter. They are pretty good for accuracy, but they're not able to do any modulation analysis. And spectrum analyzer is a little bit better than power meter and frequency counter. They are okay. I mean, they're good to do amplitude accuracy, but they are also can do measurement coverage. They can do a TOI, SHI kind of measurement, but they cannot do modulation measurement. And the last one is the vector signal analyzer. They can cover most of the measurement you want to do. Like you have a better amplitude accuracy. You can select different modulator analysis. You can do dynamic run like a linearity measurement, TOI, SHI. So the vector signal analyzer can cover most of the receiver signal analysis purpose. And of course, more functionality, more cost, right? And more challenging. So in the generator side, remember the frequency synthesizer, they are used to be, most of the time the common application is doing the local oscillator. They try to develop for up and down conversion. And then the single signal generator, like a CW generator, they have modulation built-in function, but they cannot do a really high bandwidth digital modulation. Only the vector signal generator can do the the high bandwidth kind of modulation generation. So here's another idea how the vector signal generator equipment look like in block diagram. So you have digital, right? We have baseband, and we using the direct conversion to generate the digital signal to analog signal and up converter to the RF frequency. But this one you see there's no phase shift and no LO, right? And only a single LO on here and single LO here. But you see the RF base, you basically you're doing the direct conversion to RF frequency to intermediate frequency, and then you're using intermediate frequency to up convert a way higher frequency. If you're using a direct conversion, you cannot generate a RF frequency above maybe less than 20 gigahertz. Right now, some of the vendors, they try to generate a direct conversion up to 20 plus. But if you want to generate a 60 gigahertz or 100 gigahertz, you have to use an intermediate frequency stage and using another state to up convert it. Okay, so again, so more functionality, more powerful, more cost money. So, and you will see here, right? Different method have a different issue. Like you're using a direct conversion, remember you're using a direct conversion to generate a high frequency, you have IQ impairment. And IQ impairment also have other term called LO leakage and image suppression. So there are IQ impairment issue. And when you have a IF base, like you have another up conversion method, you have dynamic range challenges. So that means your system linearity will be degraded by adding more conversion stage. So different architecture have different challenges. So it really depends the application purpose. And direct conversion is simpler and lower cost. And multi-state filtering is cost more money and you're also facing a different challenge. And more expensive too. So this is another example of the direct IQ modulation. So I keep talking about up converter, down converter. So why we want to do up converter, down converter? So let's say you try to do a signal analysis, right? You want to do a signal analysis in DSP. So most of the digital data analysis in low frequency. And if you try to analyze the signal up to 20 gig directly, it's way challenging than you're doing the data analysis close to DC. So this come out the concept, you try to down converter your signal, try to analyze to close to DC and doing the analysis. And you try to send the signal out, you try to up convert the signal to particular carrier frequency, you try to transmit. So this come out the concept of up converter and down converter. So yeah, here's a why down converter, right? So it just require more cost and more money to doing it. So here is another example. Let's say you try to do a 20 megahertz analysis for the signal at 2.5 gig. If you don't do down conversion, you have to do the acquisition from 0 hertz up to 2.5 gigahertz. But if you're just doing the down converter, you can move this signal only 220 megahertz away from your DC. So you only need less than plus minus 20 megahertz bandwidth to do the data analysis. So this is why we want to do the down converter. So this is called the frequency shifting frequency, another term called mixing. So we try to use the local oscillator to mixing your signal you try to analyze to create the signal next to the DC. And then we can do the signal analysis. And we don't need to pay the money to analyze a lot not useful data. So how the down converter architecture working, right? So in down converter architecture, there's a single conversion and multiple conversion. Single conversion is mean how many mixer and LO you try to change the intermediate frequency. So let's say single conversion, that means you only have one final IF frequency, intermediate frequency, before you're doing the data acquisition. And this is the direct conversion method. Direct conversion also has a term called zero IF. When we say direct conversion, it means we analyze all the signal close to DC. There's no intermediate frequency conversion, so it's called zero IF. And this is a multi-stage receiver architecture. Remember, we have single down converter. We also have multi-converter. When you have multiple conversion, there's another term called super heterodyne. And the concept, you try to analyze the signal to different IF frequency with different filtering to try to maintain the quality of the signal analysis. And at the final IF frequency, you try to use the digitizer to do the data analysis. So you're using a multiple local oscillator. Remember I mentioned using a super heterodyne or IF down converter, you have dynamic range challenge because your filter will degrade your dynamic range, and you go through multiple mixer, your dynamic range or linearity will be degraded. So you have to be really balanced about your dynamic range and your linearity using multiple state conversion. And most of the components, they are really expensive, so this is why it costs more money. And in spectrum analysis, they also have one other particular receiver called spectrum monitoring. So you try to analyze the signal on the air, right? Using the antenna, it could be a lot of junk. How you maybe you just try to catch a particular signal, but there's a lot of signal bundle it, and you don't want to analyze those junk. So this is why you have a pre-selector. The pre-selector is like a tunable filter. So you can tune your filter to particular target frequency to make sure your input signal is clean. And then you can do the spectrum monitoring. And thinking about you try to analyze signal from 0 up, from 1 gig up to 20 gigahertz. That means your pre-selector need to be able to tune from 1 gig to 20 gigahertz with certain amount of bandwidth. It's a really expensive component, and they are pretty sizing. They could be really big. So it's a challenge. You need to find a good one and an affordable one in your design. And another thing is when you have a lot of front-end component, you can actually improve some of the noise figure. If you have a pretty good preamplifier with noise figure, you can use this one to do a noise analysis, to do a noise figure measurement. Noise figure is another terminology in RF. I don't know I have covered this one. So basically telling you how much noise your system generated if you have an input signal on top of your original signal. So noise figure lower, that means your additional noise on top of your signal analysis is minimum. So that means you can recover your original signal, try to analyze. So lower noise figure is better. Of course, lower noise figure components mean more expensive and more challenging. Yeah. Okay, so it's the dynamic range. Remember we talked about all the harmonic stuff. They all hold our dynamic range. So when you try to analyze a signal, like this single CW signal or like a two signal, you create a lot harmonic, second harmonic, or spur, and you're increasing the signal in particular amount of power. Your device start to complex. You're not able to measure your input signal correctly anymore. So those all inside the dynamic range catalog. And I think I covered some of this already, like harmonics and phase noise. And spurs means just like you have additional signal when you have a generator signal or when you're trying to analyze some signal you don't want. And this one is the dynamic range chart with your mixer level. You will see some of the data sheet like a mixer. They can tell you what kind of power level you can hit the best linear mode and what kind of power level your mixers start to have more and more distortion products. Okay, and the last subject is VNA. VNA is It's different than transmitter or receiver. They can be done both. So VNA is not just like a generator or receiver. They can be also like a directional coupler. So it's like a master box can do a lot of functionality. So this is why they are pretty big and very expensive. And in VNA, they also have scalar and vector. That means you're doing the spectrum measurement only, magnitude measurement only. And vector means you can always measure phase. So what's the benefit of using VNA, right? So VNA, one of the most useful applications is to measure all the S parameter. So you consider a device with input and output port. You can measure the gain. It means the insertion loss. It means the output signal minus the input signal. And you can also measure the reflection, like input return loss. That means your signal forward, but you have certain amount of power reflects back. And same thing on the other side. So this comes back to the concept, the reflection coefficient. You have a signal going in to your device, and only put certain amount of transmitter signal can go through, and some power reflects back. And you're using VNA to measure those stuff. So here's the idea, right? You have a sinusoid signal go through this impedance interface, and some of the signal going back, and some signal going out, but it degrades the amplitude. And why we using VNA? Sometimes you can use VNA to characterize some of the issue. Let's say you have a cable. Your cable is broken, or some of the loose wire inside in the middle, and you can use the time domain to using the VNA to characterize the time domain, and you see a glitch or a pulse in the time domain. That means your impedance or this transmission line is not consistency matching. Something happened in this cable. So people, this is why they like to use the VNA to characterize some of the hardware issue. And this is why the time domain using to do. Yeah, VNA is a little bit more topic, can talk a lot. So this is all I have today.
Okay, thank you. All right. I would like to ask you a quick question.
Yes.
And it has a bunch of things in it. First of all, can you tell us briefly, just these are for our students, what does your company do, what you do, if you accept any interns, and then also what do you expect from our graduate students?
Yeah, so I work in National Instrument. I'm in the R&D group in Santa Rosa. And I have been working a lot of high frequency receiver and transmitter. And my current project is working in 5G. I mean, people heard about a lot in 5G, but there's a different definition for 5G. The one I work in is the future cell phone 5G. So that means when you're using 5G, right now you see a cell phone, the bar always show 4G, right? We start with LTE, 4G, and hopefully in the near future you will see a cell phone with a 5G logo on the bar. That means you have a wider bandwidth, and with wider bandwidth, that means you can do the streaming and data analysis way faster. So let's say you can see YouTube, you can load the YouTube in 10 seconds right now. Probably in the future you only need less than 1 second. So this is one of the benefits of using 5G, and also 5G can do a lot of media device data communication. So it will give you a lot of convenience. Like you have a AI homes, you can use a 5G network to control any single device, and you can do the streaming at the same time to watch video, to play video game, and without any glitch or stopping. So this is the project I'm working in right now.
As far as the interns, I mean, does your company accept interns?
Yeah, so this year I don't think we have intern because it's past the summer, but every summer we usually have 1 or 2 opening, but we are not always want hire one. It depends on the schedule. Like working on 5G is very busy. We don't have enough resource to train the intern, but we do want some helper. Like NI is you heard about LabVIEW, right? We develop our hardware. We use LabVIEW a lot. we're using LabVIEW to characterize and development our V&V plan, the verification plan for our hardware design. So we are heavy duty on using LabVIEW. So if you have a LabVIEW like a associate certificate, or you put it in LabVIEW, it will be a plus to join NI. And our new hire, the first 2 weeks just learn the LabVIEW by themselves. So all the new hire to our company, we just put them on the cubicle and give him the material and don't talk to him for 2 weeks. So
and other than the LabVIEW, what other things do you expect from our graduate students?
I mean, because we are in R&D department, we really care about the hands-on experience. So if you know how to use VNA or Cisco and some of the spectrum analyzer, it will be easier to catch up when you join our group. And plus your LabVIEW skill, you can skip the first 2 weeks learning. And then you can start coding to control our hardware to do more management right away. Yeah.
Okay. It's now about 20 minutes past, but let's just appreciate what he's doing for us. I mean, basically went beyond the 1 hour because he wanted really to, share with you some of the important information and so on. So it was really very instructive, I'm sure, for all of us, and let's give him a hand there.